Welcome back, everybody. So today we're going to be talking about single qubit universality. And in particular, what we discussed last time was we showed how single qubit rotations can be used in order to implement any unitary transformation that we feel like on a single quantum bit. That is to say, any valid quantum transformation can be expressed as a sequence of 3 rotations. Now, there was a big challenge with this because it wasn't a very realistic computational model that we assumed when we gave ourselves the ability to do single qubit rotations, basically as one of the fundamental gates. And the reason was because of the fact that the single qubit rotations basically took in an arbitrary real number as input, i.e. the rotation angle that you wanted to carry out. This is extremely unrealistic because any actual rotation would take an infinite number of bits in order to specify. So what we'd like to be able to do is we'd like to be able to reduce this to a finite gate set. And so that's the whole point of today's lecture. So let me begin by kind of reviewing a little bit of some of the formalism that we'll need in order to understand this. So make a new deck. Should have done this beforehand. Deleted. All right, cool. So very first thing that I wanted to talk about is just, if you recall, what the RZ gate is defined to be. So the RZ gate is defined to be e to the negative I z RZ of theta over here is R of Z theta divided by 2, which is equal to, it's defined to be the sum from j equals 0 to infinity, negative I z theta divided by 2 to the j over j factorial. And when you go through and use the identity that z squared equals the identity, then you'll end up seeing that the odd and the even terms group together. And this is of the form cosine identity minus I sine theta over 2, theta over 2c, which of course is the matrix e to the I theta over 2, e to the, actually that's minus e to the plus I theta over 2, 0, 0. Now, one of the things that I want that's really neat about single qubit rotations is that they can compose really elegantly together. So RZ of theta, RZ of phi, this is just equal to e to the negative I z theta over 2, e to the negative I z phi over 2, which is equal to e to the negative I z theta over 2 plus phi over 2. And why is it that these rotations end up adding? Well, in the case of Z rotations, you can see this actually in a number of different ways. So the way that I'll explain it right now is actually just in terms of these matrices. So if we express the two matrices, we have e to the negative I theta over 2, 0, 0, e to the I theta over 2 times e to the negative I phi over 2, 0, 0, e to the I phi over 2, which of course is equal to e to the negative I theta plus phi divided by 2, 0, 0, e to the I theta plus phi over 2. So these are the rotations that, or this is a property that we end up having for rotations. And in general, the property for any matrix, that's at least a normal matrix, we have that e to the a theta, e to the a phi is equal to e to the a theta plus phi. And you can see that just by assuming that if a is equal to, can be diagonalized, which is true for any matrix that's Hermitian, unitary, or almost every matrix that we really run into. These matrices are called normal matrices. They can be written in this particular form, where U is a unitary matrix. Or in other words, this is the diagonalizing transformation to it. Oh, and this should be a D over here. And so from the reason why you can end up seeing this is that this is, of course, equal to e to the u d u dagger theta. And this is, of course, equal to u d u dagger phi. Now, using the property that I asked you to prove on the homework, this is equal to u e to the d theta u dagger u e to the d phi u dagger. These two cancel, and we end up seeing from the same argument that we had up here that this is equal to u e to the d theta plus phi u dagger, which then goes back and proves our initial point once we substitute the rule backwards. So this shows that we can kind of compose these rotation-like operators together. And a way you can kind of visualize this is that what these rotation operators do is they'll take a particular state over here, and they really actually can be viewed as carrying out a rotation of theta of that state about the z-axis. So in particular, if we had a state like plus over here and minus up here, where plus is equal to 1 over root 2, 0 plus 1, and the minus state is equal to 1 over root 2, 0 minus 1. The z rotation literally actually kind of will rotate the plus state up towards the minus state. And so that's why it's a rotation, and it satisfies actually all of the algebra that you would normally expect with it. Is in like you do 2 rotations, and this angle will be increased again by theta, and the total angle from those two would be 2 theta. So that's some of the intuition for these types of operators. And we're going to be using some of that intuition in our proof to show universality for a discrete set of operations. But what are those discrete sets of operations that are the discrete operations we're going to be using? So the discrete operations we're using is T, H, T, H. Okay. Now, to give you a little bit of an intuition behind this, basically, we can end up viewing the T gate, as you recall, which is just 1, 0, 0, e to the I pi by 4, which up to an irrelevant multiplicative phase, well, okay, I'll write in the irrelevant multiplicative phase, but e to the I pi by 8, e to the negative I pi by 8, 0, 0, e to the I pi by 8. This gate over here ends up being equivalent to this, e to the negative I pi by 8, 0, 0, e to the I pi by 8. Because as I mentioned last time, this is an overall constant factor multiplied by the unitary. And constant factors of unit length do not change any quantum operation. So this we can safely drop without loss of generality. It does not affect anything. So we drop that factor, and then what we have is we have this particular transformation. Now, if we want to be able to kind of express this or think about this more conveniently, let's go back. This actually ends up being exactly of the same form as this operation over here. And so we can end up saying that t is equal to r z of pi by 4 using that previous notation. Now, the S gate over here is, or sorry, the H gate, if you recall, HTH then is equal to H RZ pi by 4 H, which is equal to H e to the negative I Z pi by 8 H, which is equal to e to the negative I x pi by 8, using a property that u e to the a u dagger is equal to e to the u a u dagger, and the property that h x h is equal to z, where x is the Pauli operator equivalent to the NOT gate, and z is, well, the Pauli z operation. So we have that this is true. So we can end up viewing this as a sequence of two rotations about different axes. This can be viewed as just e to the negative I z pi by 8 e to the negative I x pi by 8. So you might be really tempted to say, well, why can't we just merge these under a common exponent like we did before? Like, is this equal to e to the negative I z plus x pi by 8? And the answer is no, it's really, really not. Because this rule for being able to add the matrices in the exponent will end up working when the two matrices end up commuting. And two matrices are said to commute, in this case, if x z is equal to z x. So as in the order of the two operations doesn't matter. Such matrices are said to commute. In this case, x and z, well, they don't commute. They in fact anti-commute, because xz is actually equal to minus zx. So this means that we can't use that elementary rule that normally ends up applying for algebra. Obviously, if we had two z's together, like we saw previously, this would work just fine. But because one is a z rotation, one is an x rotation, we can't simplify this directly. And actually, that's going to be one of the key properties that we're going to take advantage of. So the idea basically is, because these angles don't add, our proof for universality is going to follow the following steps. We're going to first show that HT, TH goes to a rotation that's of the form e to the I minus IA delta prime, where A squared is equal to 1. So it's very much like a Pauli operation in this case. And what we're going to want to do is we're going to want to show that delta prime is irrational. And that's going to be very important for our proof, because basically what that's going to guarantee is that you're never going to run into a power of this operation such that this value of delta prime will end up being 0 mod 2 pi. Or I should say, not that delta prime is irrational, but delta prime divided by 2 pi is irrational. Okay, then once we've done that, the next stage in this is to be able to show that if we end up taking e to the negative I, let's change this notation here rather than delta prime. I'm going to call this angle theta. So e to the minus a theta times n, e to the negative I a theta m, what we would like to be able to show is that there exists n and m such that this operation is equal to e to the negative I a. Well, of course, this is theta n plus m mod 2 pi. And the reason why I put mod 2 pi in there is because of the fact that if we have this a, because it squares to identity, this is equivalent to a rotation operation, we'll see. And thus the angle, we only care about modulo 2 pi. So the idea basically is that these two phases, they'll combine together in order to form a net rotation angle. And what we want is this rotation angle, we want to be able to spin around in such a way so that we're going to generate from these two rotations a small rotation angle about this A axis over here, or about this A matrix. So we're going to generate a really tiny rotation of size, I'm going to call it now delta prime. Okay, where ideally we want this to be really tiny. And we're going to prove using this property that this angle delta prime is greater than 0, but we're going to be showing that it can be chosen, or we can always find an angle so that it can be as small as we'd like. Then the next step in this argument is going to be, well, okay, what we can do now is that we can end up actually doing e to the negative I a delta prime z e to the negative I a delta prime z. And what these z gates are going to do is these are going to cancel everything out in A that isn't the z component, we'll see. And then the result will end up being basically some angle that's going to be of the form e to the negative I z epsilon plus order epsilon squared, where epsilon is it's going where epsilon is going to be a upper bound on delta prime. Okay, so that is the steps behind it. Then once we've shown that we can make this small rotation of this particular form, we're going to basically try to make an arbitrary z rotation through an angle, I don't know, of something like, let's say 3 pi by 4 as a particular angle. So let's say we wanted to make that. What we will do is we'll use this trick, these sequences of steps, in order to turn this big rotation into a sequence of very small rotations. And we're going to pick them in such a way so that when we carry out all of the rotations, the total error that we have in all of these is going to be small. So this will end up showing that what we can do is we can chain all of these extremely small angle rotations together in order to make an arbitrary big rotation while still having a small error. And that's the big message about it. And the total number of gate operations needed to do this will scale like 1 over epsilon, where epsilon is the target error that we would like to see in the final rotation. So this ends up showing that we can build an arbitrary z rotation accurately with these steps. And then from that, the material that we covered last time will end up showing us that we can do an arbitrary x rotation and in turn, any unitary transformation on a single qubit. So that's the sketch of the proof in case you guys zone out a little bit on these next couple of steps. But I try to pay attention to it because these are some actually really useful concepts theoretically to understand why exactly a quantum computer ends up being universal, or how we can actually build an arbitrary quantum transformation in principle. So that's the idea. Now, in order for us to go through and understand many of these properties, let's take a look again at the T-gate. So the T-gate is e to the negative I z pi by 8, as we mentioned, up to a global phase. Expanding this out, this is cosine pi by 8 minus I sine pi by 8, using our favorite identity that we've been using to death in this course so far. Now, similarly, HTH is equal to cosine pi by 8 identity, this should be a z, minus I sine pi by 8, HZH, and this, of course, HZH is equal to X. So these are our two operations. And so we can figure out what the product is between them pretty straightforwardly. So THTH is equal to, well, cosine pi by 8 identity minus I sine pi by 8 z times cosine pi by 8 identity minus I sine pi by 8 times poly x. Now, when we rotate, recall the multiplication table for poly operators. We have that x squared is equal to identity, z is equal to iy, zx is equal to minus x. Sorry, actually I got this backwards. It's zx is equal to iy, and zx is equal to minus xz. So these rules end up holding, and they'll help us simplify this product. Going through and just multiplying the first term times the first term, and then the first term times the second term, like we ordinarily would do. This gives us cosine squared of pi by 8 times identity. Then we have minus I sine pi by 8 cosine pi by 8 poly z plus x minus or plus I sine squared pi by 8 y. Okay, now the reason why it's y here is just using this product rule, or this part of the multiplication table for x and z. And so we get that expression. Now, the next fact that I want to claim is claim for all a, b, and c in the real numbers that ax plus by plus cz squared is equal to a squared plus b squared plus c squared identity. Okay, now we can prove this really easily. Let's just expand the product out. Expanding the product out, we end up getting, well, ax squared plus ab xy plus yx plus ac xz plus zx plus b squared y squared plus bc yz plus zy plus so on and so forth. Okay, so first thing to note is recall the last property in here. Poly operators are they anti-commute. So if we flip the order of two poly operators, we end up getting a minus sign. So these two, using that rule, cancel. So do these, so do these. The only ones that are left are the x squared and the y squared. Now these all square to the identity. So therefore, this is equal, as promised, to a squared plus b squared plus c squared identity. Okay, so why did I do that? Well, the reason why I ended up doing this is actually just the following. We have that TH is equal to cosine squared pi by 8 minus I cos pi by 8 sine pi by 8 multiplied through by x plus z minus sine squared pi by 8 times y. Okay, now this operator is exactly of the same form that we had before. So let's write A equals cosine pi by 8 sine pi by 8 x plus z minus sine squared pi by 8 y divided through by square root of 2 cosine squared pi by 8 sine squared pi by 8 plus sine to the 4th pi by 8. Okay, and this, from our previous claim that we just showed, satisfies that a squared is equal to 1. Furthermore, or identity, I should say. Furthermore, this whole operation actually can be written in the form cosine theta identity minus I sine theta A, where theta is equal to the arc cosine of cosine squared of pi by 8. Now, it's not entirely obvious, but it can be checked that this number, which I think is something close to like 0.548, this number is actually, it turns out, an irrational multiple of 2 pi. So theta divided by 2 pi can be shown to be irrational. And why is that important? Well, the reason why it's important is, well, I guess this is just one more second and you'll see why it's important. So now we have this particular operation. A squared is equal to identity. So if you recall our proof that if A squared is equal to identity, then from a Taylor series expansion that we've done like to death, e to the minus I a theta, which is equal to the sum from j equals 0 to infinity, negative I a theta over j factorial to the jth power. This is actually just equal to cosine theta I minus I sine theta A. So this actually matches. So the operator that we build with these three products can be written in this form, e to the minus I a theta, where theta is this irrational angle. So if we, the key point behind this is that if we apply TH to the mth power, this, using our previous arguments, is equal to e to the negative I a theta to the nth power. And by repeating this argument that we had up here for how to exponentiate or how to square a rotation, we can end up seeing that the result we get in the end is just e to the negative I m a theta. Cool. All right, and why is this relevant? Well, this is really kind of important because the fact that The values that we end up getting over here, because the angle is because of the same expansion that we had before, this is equal to cosine theta I minus I sine theta A. Times m here inside the sign. Now, because this is irrational, what we know is that this will never be periodic. So for all m and m prime, m theta mod 2 pi will not be equal to m prime theta mod 2 pi. Because, well, it's an irrational angle, it doesn't define it. And if it was divided, these two were equal, then we could end up seeing that they have to be rational multiples of 2 pi. And that is not cool because, well, the angle theta is irrational. So we know that we can't have two of them that are equal. But the question is it possible to end up having two of them that are close? And in particular, arbitrarily close to zero. So, and we're going to need this in order to be able to show that we can generate these small angle rotations needed in order for this universality proof to go through. And the answer is we can. The way that we're going to do this is let n be equal to 2 pi over delta, where here delta is a kind of like smallness parameter. What we would ideally like to do with this is we would like to be able to find from this two rotation angles that are very close to each other. And the reason why we want to be able to find two values that are close to each other is because we can use this in order to subtract them to end up finding a tiny rotation. So this value of n here is 2 pi over some smallness parameter delta that is going to talk about our target size for this tiny rotation we're going to want to build. And we're going to assume that we have two integers, n and m, element of the interval 0 to n minus 1. Now, the claim that I'd like to make is let theta k be just equal to k theta mod 2 pi. I'm just doing this because of the fact that we need to do all of this in terms of modular arithmetic, and I really just don't want to have to worry about the 2 pi rotations over and over again. Further, because of the fact that these are irrational and no two are identical, we can end up assuming that these angles between 0 and n minus 1 that we get assume, without loss of generality, that we sort these angles, let's call these sorted angles, theta k, such that theta tilde k is an increasing sequence. Furthermore, let's take, without loss of generality, theta tilde of 0 to be equal to 0, just for convenience. Okay, cool. So now that we have this increasing sequence of sorted rotations that we end up getting out from this, let me make another claim. For every delta greater than 0, there exists n and m in 0, n minus 1, such that n times theta mod 2 pi minus m times theta mod 2 pi is less than delta. Okay, in order to prove this, we're going to prove this, unfortunately, by contradiction, which is often like the worst proof technique because of the fact that it is extremely powerful, but it conveys less intuition than I would often like for it. So we're going to prove this by assuming the opposite. Actually, let's make it less than or equal to. So we will have from this that we're going to assume in our proof that for all n and m, theta n minus theta m is greater than delta using the notation that we had before. Okay, cool. So then in particular, if this is true for all n and m, then it's definitely true that theta I minus 1 is greater than delta as well. So what this ends up meaning is that let's take a look at the largest value of theta mod 2 pi that we have. This will be theta n minus 1. This is equal to, well, it's equal to theta n minus 1 minus theta n minus 2 plus theta n minus 2 minus theta n minus 3 plus all the way down to plus theta 1 minus theta 1. Okay, so I've done absolutely nothing here except just telescope this sum out in order to bound it. And so what I'd like to do next is I'd like to lower bound this particular sum. So I can lower bound this by using this and the fact that theta I is an increasing sequence. So therefore, theta I minus 1 is greater than delta. So if that's the case, then we can end up going through this and seeing that the result is actually just n minus 1 times delta, or greater than or equal to, no, sorry, it's strictly greater than. Now, n, if you recall, is equal to 2 pi over delta minus 1 times delta, which is equal to 2 pi minus delta. Okay, but what we have here is we've got a unit circle, and this angle mod 2 pi that we have for the last point over here has an angle that's greater than 2 pi minus delta. So this angle in here has to be less than or equal to delta. But we assume that this is theta 0. So theta 0 now has to be closer to theta n minus 1 than delta. This is a contradiction. And thus, the claim follows. So, simple proof by contradiction that if we pick these n rotations, we're always going to find at least one or two values that happen to be close to each other. And again, we can't have any of them be precisely equal to each other, which would ruin everything because of the fact that they're irrational. Or the theta value of theta is an irrational multiple of 2 pi. All right, so now that we've built all of this up, we can now go forward and do the last step in all of this. So we've got now a small rotation, and the way we can always build this small rotation is, okay, if let theta n and theta m be the two such that we have e to the negative I. Okay, yeah, be the two that are within distance delta. Then what we know from this is that e to the negative I a theta n, e to the I b theta m, or sorry, not b, this is a over here, is equal to e to the negative I a theta n minus theta m. And this over here is an angle delta, which in magnitude is less than, or I should say delta prime, which in magnitude has to be less than delta from the previous claim that we made. So this ends up generating a small rotation angle through it. But the annoying bit is that we want RZ. Instead, we've got this funky operation A kicking around instead. And we'd like to figure out a way of converting this A operation into something that looks like a Z rotation. The way that we're going to do this is as follows. What we can end up doing is once we've subtracted these two operations from each other, what we can do is we can build the RZ operation just by actually Taylor expansion. So by Taylor expanding e to the negative I a delta prime, this is equal to I minus a delta prime a plus order delta squared. And this just comes from a second order Taylor series expansion again of the exponential. Now, recalling our definition of A, this is identity minus I delta prime cosine pi by 8 sine pi by 8 x plus z minus sine squared pi by 8 y divided by the square root of blah, 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 the other normalizing stuff, and plus order delta squared. Okay, so now the question is, what happens if we multiply this by e to the negative I a delta prime times z e to the negative I a delta prime z? Well, there's actually some pretty neat things that end up happening. Recall that because poly z anti-commutes with x, we have z x z is equal to minus x z squared equals minus x. Similarly, using the same anti-commutation property with y, we have that this is equal to minus y. So the z conjugation is going to flip the sign of this and this, but z cubed is of course equal to z times identity is equal to z. So this will stay exactly the same sign. So when we expand this out, we'll end up getting I minus I delta prime cosine pi by 8 sine pi by 8. And then we're going to get the sum of these two arguments. One from this one that'll have the x and flipped, and the other one won't. So we'll get x plus z from the first order Taylor expansion of that minus z plus x, or minus x plus z, and then we are going to end up getting a minus sine squared pi by 8 plus y minus y divided by square root and plus the higher order correction terms. We can see now that the second order, the x's cancel out. leaving only the z terms. And this ends up leading to a rotation that we end up getting that has an angle. So this we can end up seeing is an angle that's of the form r I minus 2 delta prime cosine pi by 8 sine pi by 8 divided by the square root of 2 cosine squared pi by 8 sine squared pi by 8 plus sine squared, or to the fourth pi by 8. And then there's correction terms that are that scale like delta squared. So this is equal to our z of 4. Oh, and this is now just a z because that's the only operation that's remaining. This is equivalent to rz of 4 because of that annoying factor of 2. Delta prime cos pi by 8 sine pi by 8 divided by this normalization constant plus order delta squared. Okay, fantastic. So now if we repeat this process, if we want to use this rotation to end up generating a large rotation, what we can end up doing is we can repeat this. Let's call it, okay, actually, yeah, I guess a simpler way for me to express this is let me express this as RZ of delta prime omega plus order delta squared. So if we want to be able to build a large rotation, let's say we want to build a rotation through an angle of order, okay, let's say we want to build a rotation through an angle of phi. Okay, well, then what we can do is we can actually just raise this to an angle of phi divided by omega delta prime, which when we expand this out ends up giving us our z of delta prime omega times phi over omega delta prime. And then just using the binomial theorem, we can end up seeing that the first order correction term is going to be order delta squared phi divided by omega delta. Because again, delta prime is less than or equal to delta. So we end up getting that, those guys cancel, and we end up seeing that the remainder from this ends up being order delta. Now, the cost for finding this rotation was an application of HT or THTH order n times for the first rotation. And by first rotation, what I mean is when we were trying to do this to build the small angle rotation, this one is going to be order n operations, and this one is also going to be order n operations, where n is order 1 over delta. So therefore, this whole thing can be done using a number of gates that scales like order 1 over delta, which shows that we can build a arbitrary single qubit rotation within air delta using order 1 over delta operations, and thus completing our proof. So that is that. This shows that we can do single RZ rotation. Now, the final step, just to remind you, for single qubit universality is that that any unitary, of course, can be written as e to the negative I alpha, rz of beta, rx of gamma, rz of delta. So if given that this is true, we've now got a prescription for building each of these operations with an arbitrarily small error. Rx, as we mentioned before, is no different than HRZH. So therefore, by repeating this whole thing, or each of these operations order n times, we end up getting a cost as order 3n, which is equal to order n. So that is how we can end up showing that an arbitrary single qubit rotation, and in turn, an arbitrary unitary transformation on a single quantum bit can be implemented just using those two gates fired in a sequence over and over again. And there you have it. So now that we've done this, you understand more than probably you would like to about single qubit quantum computing. Next, we're going to go on to multi-qubit quantum computing and proceed to prove that that quantum computers, or at least this gate model of quantum computing that we've discussed, is universal for general quantum systems that are more than just one bit. So thank you very much, and I look forward to seeing you next time.